Look around any modern city. You are looking at a world built almost entirely out of steel and cement, the structural foundations of human civilization. But forging those raw materials comes with a massive cost. Heavy industry alone is responsible for roughly a quarter of all global greenhouse gas emissions. The pressure to clean up this sector has triggered a global race to produce what's being called green steel. The problem, however, is that almost no one can agree on what green actually means. Before we can physically decarbonize the industrial world, we have to establish a strict scientific baseline for what counts as clean. Enter the International Energy Agency. To prevent greenwashing, the IEA has proposed a robust, standardized definition for what they classify as near-zero steel. The IEA threshold operates on a sliding scale, with the target emissions shifting based on exactly what materials are fed into the furnace. At the cleanest end of that spectrum, you have steel produced entirely from recycled scrap metal. Looking at this sliding scale, using 100% scrap limits emissions to a tiny 50 kilograms of CO2 equivalent per ton of steel. However, the global supply of scrap metal is finite. It cannot meet the massive surge in infrastructure demand alone. To satisfy that growth, we must extract raw iron ore to create primary, brand new steel. This chart compares those two extremes. Notice that for 100% primary iron, the IEA's strict near-zero target is significantly higher, allowing for up to 400 kilograms of CO2 per ton. That means even if a global steelmaker perfectly hits the IEA's ambitious targets, creating new steel legally guarantees leaving hundreds of kilograms of carbon in the atmosphere. Why is that primary threshold set so high? Even with the best energy optimizations in the world, why can't we get that 400 kilograms down to zero? The answer lies inside the intense, hyperheated environment of the industrial blast furnace. When we think of industrial pollution, we usually think of the coal or natural gas burned simply to get the furnace hot enough, but that is only part of the equation. This molecular animation shows the real bottleneck. Raw iron ore is essentially iron bound to oxygen. To purify it, carbon is introduced to strip that oxygen away. The inevitable result of this chemical reaction is carbon dioxide waste gas. You cannot engineer around this. Because the emissions are a direct byproduct of the core chemical reaction, we can't just maximize our efficiency to reach zero emissions. If the creation of carbon dioxide is mathematically unavoidable inside the furnace, the only remaining option is to intercept it before it leaves the smokestack. This is where companies like biogenic Urja are focusing their engineering, targeting the exact hard-to-abate sectors that struggle with this chemical bottleneck. For decades, the default idea for carbon capture was to trap the gas and inject it deep underground, a process that is expensive and yields no usable product. Biogenic Urja takes a different route. They capture raw industrial exhaust and feed it directly into an advanced chemical conversion reactor. Instead of burying the waste, the reactor upcycles the CO2, stripping it down and recombining it into valuable carbon and hydrogen derivatives. This conversion process is the exact mechanical tool needed to close that 400 kilogram gap left by the IEA's primary steel targets. Instead of absorbing a massive financial loss, these facilities can now process their unavoidable climate liabilities into lucrative, usable assets. We are seeing a shift in how heavy industry approaches its waste, moving from simple emission reduction toward active material recovery. On one front, regulatory roadmaps from organizations like the IEA are forcing global producers to maximize their efficiency and to heavily prioritize recycled scrap metal. On the other front, technological innovations from groups like Biogenic Urja provide a structural safety net for the stubborn, chemically unavoidable emissions of primary production. By uniting rigorous global standards with advanced carbon upcycling, we are finally closing the industrial loop, ensuring today's exhaust actually becomes tomorrow's raw material.